That's
You
the
can
whole
click it
point.
too.
I think you figure out how to put it on.
There you go.
So let's talk about what's gonna happen in this lab. There's kind of two distinct parts to it.
She'll find a way.
So the first thing you need to figure out is what's the theoretical value for the speed of sound. Okay? So down here on number 9, you've got this handy dandy little equation that says V equals 331 meters per second plus, and here's your correction factor based upon temperature, 0.6 meters per second times the temperature in degrees Celsius. So the room temperature right now is 22 degrees. So somebody take 22 times 0.6 and add that to 331. What'd you get?
344.2.
3 what?
44.2.
344.2.
Yeah. Yeah, these are going with string times.
Okay? So that's the theoretical speed of sound in this room under these conditions. Okay? So you're going to need that number later on. So here's what's going to happen over here on page 2. So around the room in the back are these 3 wavelength or frequencies: 320, 426.6, and 512. Those are stamped on the tuning forks. You're going to know what the frequency is. Okay? There's no ambiguity in the frequency. It's stamped on the tuning fork. Okay? Now, what we need is a correction factor. Okay? So that correction factor is this 0.3 times the diameter, the inside diameter of the pipe. Okay? So over here on the front, this is where this becomes a part. So on an open, closed system, you take 4 times L plus 0.3 D. Obviously, what units does your D need to be measured in?
Meters.
Meters, okay? Now, so what you're going to do is you're going to take that tuning fork and lift that up. Now, what I would do is I would go like back and forth until you get a pretty good idea of where that is. So you're going to measure that length from the top of this tube to the top of that water. That's going to be your L value. You're going to measure the inside diameter of the pipe. That's what you're going to use as the correction factor. The reason that we do that is that that sound is trapped within that tube, but once it's free of that tube, is like free at last, free at last. Good God Almighty, I am free at last. And then it expands out. So that's why that correction factor takes that into account, okay? Because it actually, you get almost like a false reading because that sound expands once it goes out the top of the tube. So, over here, then you're going to have 0.3 times that diameter. Your measured value of L, okay? Then you're going to determine the wavelength, okay? So you're going to determine your wavelength from this number. You are going to try and determine the wavelength. That's the whole point of this. Then you're going to have an experimental value for the speed of sound. So then you're going to go, oh, V equals wavelength times frequency. You know the frequency, there's no ambiguity in that. This is going to generate the value of the wavelength, multiply the two numbers together, voila, there's an experimental value for the speed of sound. Okay? Cool with that? Good? Now, your experimental error is going to be your calculated speed of sound minus, in this case, what do we get? 344.2?
Yep.
Divided by 344.2 times 100. I don't need to see every calculation, but I need to see one complete set of calculations, okay? If you want to go big time and show me all of them, you can. But listen to me. At least show me one calculation of, there's nothing to calculate on L, but that calculation of wavelength, that calculated speed, and that calculation of experimental error, okay? Again, I don't need to see all of them. If you want to, that's fine. Kudos for you. But I want to see one neatly written, concise set of calculations, okay? So that's what's going to happen on those three back there. Up here, now this is where it becomes a little bit sketchy. And it doesn't make any difference in what sequence you do this. This one, you don't know what the frequency of the tuning fork is. So down here, when you get to, on this unknown one, which is this bottom of page 2, using the closed tube apparatus, determine the frequency of the unknown tuning fork, showing all calculations. In this one, you're going to assume the speed of sound is that 344.2. So you're going to do the same thing. Problem is, and no, we'll just take the gray duct tape off. You do that, I will take gray duct tape and bind you to the wall. Okay?
That sounds like fun.
Cone.
Yeah, you never.
Cone.
Shut up. Kindly.
So, the idea being is that you measure whatever you need to measure, and you have to take that correction factor into account, okay? And again, everybody's number is going to be a little bit different on that calculation of that unknown frequency, okay? Show me the calculations. Now, so in here, in this room, this is where you're going to do the 4. It doesn't make any difference what sequence you do them in, okay? If you want to start with the unknown, that's cool. There's 4 stations in here. The open one, I'm going to have over in the next room because that you really have to listen for. So with that one, you're going to set this up, and that's going to have a specific frequency. And like I said, this is the harder one to hear. But I will give you a hint, okay? On this one, on that length, when you hit that point of resonance, the entire length should be somewhere between 0.3 and 0.4 meters, okay? So that's where that goes. So if you're not within those values, you've done something wrong. Now, this one, you don't need to use the correction factor, mainly because of the fact that that whole air tube is vibrating and you have different size pipe and it's just not worth the effort, okay? So only use that correction factor of 0.3 when you're doing the open-close system. Don't use it on the open-open system, okay? So you've got all of that, and then you've got these questions to answer here. Be specific on that. When you get to that last question, when it says it vibrates in the second harmonic, so let me kind of give you a visual of what that looks like. So the first harmonic would be something like this. So the second harmonic is going to be something like that. Okay, so that's what it means by that second harmonic. So just keep that in mind. That'll make sense when you get to that problem. Okay, I'm done. You're on your own. It's a good day. 104,000 reasons why it's a good day.
Approximately what? What's this for?
That's for the one graph that you have to draw. Yeah, that half sheet of graph paper is for the one graph that you have to draw.